Hey everyone, welcome to the video replacing Friday's lecture since I'm out of town. So, for Wednesday, right, we left off on the example of y prime is equal to minus y plus f of t with the initial condition of y sub 0 is equal to 2, and then f of t is equal to 0 for 0 less than or equal to t less than 1, and then t minus 1 for t greater than or equal to 1. And remember last time, right, we rewrote f of t as the unit step function. It'll be u sub t minus 1 times t minus 1. And so here, right, we can rewrite the ODE with this new f of t as y prime. I'm going to bring that negative y on the left-hand side, so we're going to have this plus y is equal to the unit step function of t minus 1 times t minus 1. And so, right, this is ready for us to take the Laplace transform of both sides, since we can use the table now, right? We can use table entry number 1 for the Laplace transform of y prime, so that, right now we're going to, Laplace transform. So we're going to have y sub s times s minus y sub 0 plus the Laplace transform of y is just going to be capital Y of s. And then for this right-hand side, right, we have, we're going to use table entry number 5. And here we're going to have f of t minus 1 is equal to t minus 1. And so for f of t, right, wherever we see a t, we're going to replace it with, or wherever we see a t minus 1, we're going to replace it with just a t. So we're going to have just little f of t is equal to t. And write the Laplace transform of this, of f, is going to be capital F of s, right? This is using table entry number 8, is just 1 over s squared. And so with this, right, we can now take the Laplace transform of the unit step function of t minus 1 times our f of t minus 1, and that's going to get us e to the negative s times 1 over s squared. And so with our initial condition, right, we can rewrite this y sub 0. This is going to equal 2. And so rewriting the whole ODE. Actually, I want to bring that 2 on the right-hand side, right, since we want to solve for this capital Y sub s. We have y sub s plus capital Y sub s is equal to e to the negative s times 1 over s squared plus 2. And so, right, we can factor out the y sub s, capital Y sub s is on the left-hand side to get s plus 1 capital Y sub s is equal to e to the negative s 1 over s squared plus 2, right? And then we divide both sides by this s plus 1. So we're going to have e to the negative s 1 over s squared, s plus 1. Oh, that's not a good s, is it? Plus 2 over s plus 1. And so recall from Wednesday's lecture, right, we, for this first term, this e to the negative s times this fraction, we just want to ignore this e to the negative s and find the Laplace transform of 1 over s squared times s plus 1. So we can call this capital G of s is equal to 1 over s squared times s plus 1. And here, we're going to have to do partial fraction decomposition. So we have a over s plus b over s squared plus c over s plus 1. And so, doing partial fraction decomposition, multiplying the denominator on both sides, and then solving for these coefficients a, b, and c, you're going to find that a is equal to -1, b is equal to 1, and c is equal to 1. Hence, we can rewrite our g sub s as -1 over s plus 1 over s squared plus 1 over s plus 1. And taking the Laplace transform, or the inverse Laplace transform of capital G, we can use table entry number number 7 for this first term. That's just going to be -1 plus, this is going to be table entry number 8. This is just t. And then our last one, this is just table entry number 12. And that's going to be plus e to the negative t. And so, with the inverse Laplace transform of this capital G sub s, going back to our capital Y sub s, taking the inverse of this capital Y sub s, So if we take the inverse of Y sub s, this is going to equal to, for this first term, we're going to have to use table entry number 5. And so we have the unit step function of t minus 1, because our a in this case is just 1, from up here, we have this 1. And so with our, let's call this our little g of t, we're going to have g of t minus 1. So wherever we see a t, we're going to replace it with t minus 1. And then, this last term, this is just, again, table entry number 12. And that's just going to be plus 2 e to the negative t. And so writing out y sub t fully, we're going to find it's the unit step function of t minus 1 times -1 plus t minus 1 plus e to the negative t minus 1. And then we're going to have that plus 2e to the negative t. And so that is our answer for solving this piecewise ODE. Now, with this, we're going to move on to our next section. And this is going to be section 7.4, operational properties. And so we're only going to cover one of these operational properties. And this one is going to be the Laplace transform of t to the n, where n is just some integer, of f of t. This is going to equal -1 to that same n times the nth derivative of s, right? This is the same as -1 to the n times d to the n over dn, or ds to the n of f of s. So it's the nth derivative, right? And just some intuition of where this kind of property comes from. If we just have, say, some function f of t, if we were to take the Laplace transform of f of t, right, if we just assume that's capital F of s, if we were to take the derivative of this f of s, right, remember the definition of the Laplace transform. It's the integral from 0 to infinity of e to the negative st f of t dt. But remember, right, we're taking the derivative of this, so we have this ds. And so remember from calculus, we can bring in this differential operator. So we have the integral from 0 to infinity, right? This is going to become a partial derivative due to the fact that we have the variables s and t, e to the negative st, f of t, dt. And so since the only kind of thing that depends on s is this e to the negative s, we just have to take the derivative of that. So that's just going to be the integral from 0 to infinity of negative t, e to the negative st, f of t, dt. And right, this negative number, we can bring it out. And then notice that we're going to have the integral from 0 to infinity of e to the negative st times t times f of t. And that is just going to be, right, using the definition of our Laplace transform, it's just going to be the Laplace transform of t, f of t. And so bringing this negative on the left-hand side, we get negative ds of f of s is equal to the Laplace transform of t, f of t. And so kind of continuing this kind of process right here on the screen with t times f of t, and then recognizing that the derivative of f of t of sorry, let me restate that. If we notice that when we take the Laplace transform of, say, like t times f of t, and then take the derivative of that, we can kind of continue on this pattern to find that the Laplace transform of t to the n f of t is going to equal this -1 to the n times the nth derivative of f of s. And so, right, we can go through an example of actually using this property. If we were given g of t is equal to t e to the 2t, right, notice here we're going to have n is equal to 1 right here, right? And our f of t is going to be e to the 2t. And so first, right, we want to take the Laplace transform of this f of t. Well, we can just use table entry number 12 immediately, right? This is already table ready. So we would have f of s is equal to 1 over s minus 2. And so here we need to take the derivative of capital F of s in order to find the Laplace transform of little g. So that derivative, right, this is just quotient rule, it's going to be negative 1 over s minus 2 squared. With this, right, we can now take the Laplace transform of g. This is just going to equal negative 1 to the first power times capital F prime of s. And this is just going to be, right, negative 1 times negative 1 over s minus 2 squared, right? And then this simplifies to just 1 over s minus 2 squared. So now we can take the Laplace transforms of, right, t times some function of a function that we know the Laplace transform of. Just to kind of solidify this concept, we can do another example of g to the t is equal to t cosine of t. Right, again, we're going to have n equal 1, and then our f of t in this case is cosine of t. And so first off, right, we want to find the Laplace transform of little f. This is already table ready. This is just going to be entry number 13. And so, right, capital F of s is equal to s over s squared plus 1. And again, we want to take the derivative of this capital F of s. So that is, again, just the quotient rule. It's going to be s squared plus 1 minus s times 2s all over s squared plus 1 squared. And so now the Laplace transform of our little g, which is capital G, of s, this is going to equal, right, negative 1 to the first power times, right, this numerator is going to simplify to just 1 minus s squared over s squared plus 1 squared. Right, and then this is just going to equal s squared minus 1 over s squared plus 1 squared. It's going to be our final answer. So, having covered this operational property, there are two other operational properties in section 7.4, but we will in fact not be covering those. So we're not going to do convolutions. And periodic functions. So if you see those on the previous exams, you can just skip them since they're not going to be on the exam this coming Thursday. So with this, having covered this operational property, we're going to move on to our final section of chapter 7, and that's going to be 7.5. And here, this chapter is about the Dirac delta function. And so, firstly, right, when we want to model kind of an instantaneous force, so think of just like hitting a golf ball with a golf club or a baseball with a bat, or just, right, just like hitting a wall instantaneously. We want to kind of represent that as an instantaneous pulse. And so the idea, right, if we have to kind of create a function to represent this, right, this pulse, we call it this, the unit impulse function. Where we denote it as delta, a small change in t of, I'm actually going to need a little more room to write this out, of t minus a is going to equal 0 for 0 less than or equal to t less than a minus our small change in time. And then it's going to equal 1 over 2 times that small change in t for a minus that small change less than or equal to t less than a plus that difference of t. And then just 0 again for t greater than or equal to a plus that small time change. And so, right, just to kind of graph this, to get an idea of what this kind of function looks like, right? Here we have the origin, this is t. We're going to graph this impulse function. And so, right, for 0, it's going to be 0, and then up to the point of a minus that small difference of change, it's going to jump up to 1 over 2 times that small time difference. And it's going to be that up until we get to the point of a plus that delta t. And it's going to jump back down to 0. And so what's going to happen when we take this kind of difference in t to be really, really small is that this kind of function is going to, right, it's going to get smaller and smaller up to the point where we can basically write this delta of t is pretty much like, right, pretty much like goes off to infinity and then comes back down. So this is for delta of t going to 0. And so properties of us taking this difference of t going to 0, this is how we kind of get the direct delta function. Which is not really a function. Because, right, one of our properties of it, just from this graph, is that we notice that essentially for the direct delta function of t minus a is just how we kind of denote it. It's essentially 0 when t is not equal to a. Right, this jump right here is going to happen when we get to a. And then it's going to be essentially affinity for t equal to a. But this isn't really a function, right, because we can't have something equal to infinity. So instead, right, we have this representation as an integral for the direct delta function of t minus a. We just have it essentially equal 1 dt. Right, we're taking the integral with respect to t is equal to 1. And so essentially with this kind of property we can have also a sifting property come directly from this. And so this is on your table. It's one of the 4 useful formulas at the bottom. The direct delta function of t minus, on your table it's going to be t naught, but here I'm just going to have it as a, of f of t dt, where f is just some continuous function, is going to be f of a. And so the sifting property is really useful for us, since, right, if we were going to take the Laplace transform of the direct delta function, t minus a, right, this is from, remember the definition, from 0 to infinity, the direct delta function of t minus a, e to the negative st dt. But right, with this sifting function, or sifting property of our direct delta function, we're going to get that this just evaluates to e to the negative s times a. And so here, right, this is table entry number 20 on your table. And so with this, I think for next time, I will start with solving the example. We have a little more time actually, so I will work out solving this example, since some of the web assigns have you working through direct delta functions, taking the Laplace transform of that. We want to solve this ODE of y double prime plus 9y is equal to the direct delta function of t minus pi, for the initial conditions of y sub 0 equal y prime of 0, which is just going to equal in this case 0. And so with this, right, our first step is going to take the Laplace transform, because none of our previous techniques we can solve this ODE with those, so we have to use the Laplace transform. So first, let's start off with Laplace transform y double prime. That's just the first, or the second entry in your table, so that's just going to be s squared y sub s, capital Y sub s, minus s times y sub 0 minus y prime of 0. And then the Laplace transform of 9y is just going to be 9 times capital Y sub s. And finally, the Laplace transform of our right side, we're going to use table entry number 20 again. So number 20, I guess here, using the notation on the table, t naught is going to equal pi. And so we're going to have this e to the negative s pi. And so now, right, we want to plug in our initial conditions into this ODE. This is equal to 0. This is equal to 0. And so we're left with s squared capital Y sub s plus 9 y sub s is equal to e to the negative s pi. And so, right, we want to solve for this capital Y sub s. And so we would factor out an s squared plus 9 and divide by that on both sides to get capital Y sub s is equal to e to the negative s pi over s squared plus 9. And so going, right, we want to factor out this e to the negative s pi to have 1 over s squared plus 9, right? Looking at our table, This is table entry number 14, but we want to multiply by 1. So this is number 14. Right, to get this table ready, we want to multiply essentially by 1. So we would have this times 3. So we have 3. And then we'd have to bring out a 1 over 3 here. And so, right, using table entry number 14, as well as table entry number 5, we're going to find the inverse Laplace transform of y of t. Is going to be, right, 1/3 u of t minus pi times, right, our sine of 3 of t minus pi. And with that, we get our answer. And so, right, even though we started with a direct delta function in our ODE, we still end up with a unit step function in our solution. And with that, that is essentially 7.4 and 7.5. We have covered all the material that will be on the exam. And next time, I will probably start with some Mentimeter to go over these operational properties and the direct delta function. Goodbye, everyone.